morning, and thank you for joining today's webinar from Spec Innovations, Simulate Functional Models, Generate Cost, Schedule, Performance, and Resource Analytics Rapidly. My name is Taylor Duffy, and I'll be the moderator for today's webinar. First, I'd like to go over some housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through Twitter using the handle @SpecInnovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Now I would like to introduce to you our presenter, Dr. Stephen Dam. In today's webinar, Dr. Dam will walk you through scripting and simulation using Innoslate's Discrete event and Monte Carlo simulators. This will allow you to plan ahead by analyzing your system or project's cost, schedule, and performance. Dr. Dam is the president and founder of Spec Innovations, as well as one of our DODAF training instructors. He's been involved with research, experiments, operations analysis, software development, systems engineering, and training for more than 40 years. He has also received an Expert Systems Engineering Professional ESEP certification from incurs. He is currently applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send Dr. Dam any questions through the LinkedIn users group or send him an email to stephen.dam@specinnovations.com. And now I'll hand over the controls to Dr. Dam and we'll get started.
Thanks, Taylor. Appreciate it. So we're going to talk today about a variety of topics about simulation. So first of all, well, it obviously went in the wrong direction. So let's just put it up here. So first we're going to talk about why do we simulate? That's, a lot of people really ask this question all the time. In fact, I imagine a lot of your senior managers will ask you that question, and you need to have a good answer to that. Then we're going to talk about what kinds of simulation are appropriate for systems engineering, because there's all kinds of simulation that is used out there. And then I'm going to focus on discrete event and Monte Carlo simulation, not just because that's what we have in our tool, but those really are the primary ones you'll see that really fit systems engineering activities. And then how does scripting enhance simulations? That's an important aspect of it. In general, people don't like to do a lot of scripting. I know I don't, so we try to minimize that, but we'll talk to you when you have to and what makes sense when to use it and how to use it effectively. And then how costs, timing, resources, and physical constraints are used in the simulations. That's an important factor. And then finally, how do systems simulations work with design engineering simulations? So, systems engineering, we do a certain level of abstraction of the problem. Design engineers go much, much deeper in their simulations. And so we want to talk about how those fit together. So you'll hear all kinds of terms that are associated with that, digital engineering particularly. So let's jump into it. So why do we simulate? First of all, the emphasis today is on model-based systems engineering, okay? And, many practitioners are out there spending enormous amount of time modeling the system. I often ask people, well, why are you doing that model? and they say, for the most part, they're really just drawing something somebody told them to go draw. and they're using a database tool because that lets you capture the results and a number of things in terms of reuse and other things that helps you supposedly do. Well, okay, so how do we know any of these models that people are drawing are correct? And it's really through simulation of the models. That's really the methodology, the method that works. That's why it's modeling and simulation. And you hear those two come together. So model-based doesn't mean just creating the models. It means verifying and validating them through simulation to a great extent. So simulation can help us ensure, first of all, that the models are logically correct. That's a really key part of it. Do I have the correct logic? You'd be surprised how often you're doing the analysis and you run the simulation. It's sort of like writing code, right? Code compiles, and you say, oh, great, it's going to execute, and it doesn't. Okay, because something's wrong. There's some logical mistake in the code, or it doesn't do what you expected it to do. So you really want to make sure it's correct. And then if you can properly calibrate, and we'll talk about what we mean by calibrate the model, then it becomes a predictive tool for developing performance requirements. You can decide how, what the system performance might be. So again, that's another part of it. So the models often, by the way, are helping us derive and develop our functional requirements, or validating our functional requirements. The simulation helps us with those performance requirements. So simulation is also used during the V&V portion of the life cycle. So what I was talking about before, it really happens early in the life cycle as you're doing development work. But it's also a part of a way to extend test results. And it's been used forever to simulate. Particularly, it's often, in fact, the test results themselves are often the source of the calibration. And so again, it lets you explore a broader range of potential scenarios, test scenarios. And that keeps you from having to try to test everything. One of the problems we have in the software world is we test. That's something we have to do. We really don't have a good alternative, because in general, it's hard to simulate code. We can to a certain level, and we certainly can get down to a certain level of simulation of code, but it's tough. And so and few people go to that level of decomposition. I go off and just write the code. So I've been recently involved in a project where we spent quite a bit of time getting down to the code message passing level between modules, and that's was about as deep as I've ever been, and that's probably the closest I've come to doing actual simulation of software. So so what kinds of simulation are appropriate for systems engineering? We mentioned several before, but if you type that in to Google, sure enough, you come up with this, that came up with a nice little cute graphic there. All these different types of simulation: computer simulation, Monte Carlo method, of course, social simulation, distributed computing. I thought it was an odd one. I thought for why that came up with computer simulation or simulation. Merger simulation, on and on and on. So all different types of simulation. Right? So when you type in types of simulation, what are there to get this kind of list? One of the ones that also can help sometimes is agent-based, and that's another one for another time to talk about. So again, many types are available for engineering activities. Particularly design engineers are focused on physics-based modeling of detailed systems and components, okay? And they particularly look at also the broader environmental effects and things, particularly like electromagnetic radiation effects and things like that. If you, and full disclosure, we are a partner with ANSYS, and so most of the ANSYS tool set does a wonderful job of this kind of capability. So if you're looking for, detailed physics-based modeling tools, ANSYS is probably a one-stop shop. Systems engineering models processes. That's what we're mostly really doing. It's the logical processes you go through, particularly operational processes. You're going through is often what I find myself modeling most of the time, because that's where I can understand what's the functionality that the system needs. And so with that, discrete event and Monte Carlo simulations have really proven effective over the years. I've certainly been using a discrete event for at least 30 years. Monte Carlo, I found to be harder. It was harder to find good Monte Carlo simulations that would work with the modeling tools I was using. And so to create a Monte Carlo equivalent was quite painful a few times when we tried to do it. More recently with our Innoslate tool, we built in Monte Carlo, so it would be a natural outcome. And it turns out to be extremely important. And I'll get into that a little bit later when we get to talk about Monte Carlo. So let's go into what's discrete event simulation if you're not familiar with it. And probably a lot of the audience are, but there's always people who aren't. So I want to make sure everybody's on the same sheet of music. So a discrete event simulation model, again, models the operation of the system as a discrete sequence of events and times or steps. You step 1, step 2, step 3, you hear that all the time, or a process model is another way. It's also sometimes called a behavioral model. You hear that terminology. And so I'm using that here. And since the behavioral model is a set of these steps, these events, that require a certain amount of time to complete, a discrete event is used to step through the model. Okay, so you can, a discrete event sim, you know it by the fact that it has a step option. Almost every one of the discrete event simulators I've ever seen has a step option. You can actually literally step each step at a time if you want to. Most people don't, unless they're debugging it and trying to work through finding where problems are in the model. But that's certainly a way you can execute and see what's happening at each step. And then what that does is then you want to accumulate the overall impact dynamically to calculate that resulting time and any other parameters that you might need for the system operation. So there's lots of things you would want to see in this kind of simulation to understand what the system can and can't do. And so again, as I mentioned, the executing step by step is aid in the debugging of the simulation. So if you think about how do I do that sometimes in code, I have a debugger, and that's what it does. It basically, I can set breakpoints someplace, and I can go through and walk through it. Unfortunately, we don't have breakpoints as an option in here, but you can see. Usually, you can tell pretty quickly when you get to a point. And you can always have write statements and things like that to the console. So again, I'll talk about that a little bit more here as we get into scripting. So what's Monte Carlo? Again, most of you are probably very familiar with Monte Carlo. So Monte Carlo is used to model the probability of different outcomes in the process because there's variance. There's some kind of random variables that are a part of the simulation. And this is particularly the case because a lot of what we're doing in modeling, we're modeling people's behavior. That's another reason it's called a behavior diagram sometimes. You know, that behavior of the system, it's behavior of how the people interact with the system. And so people certainly have random capabilities, right? Some people are very quick to respond to something and some people aren't. And so oftentimes you have to represent that range of people who might operate your system in a distribution of some kind. Or it might take vary in an operation, it might take longer sometimes when there's a lot of data. Other times when there isn't, it has less, and so again that might be a range. So duration of even a step by equipment can also have potentially distributions associated with it. Random variables again happen in the process model in decision points and distributions in time, resources, and costs, particularly. So you'll see that, and again, we have that ability to add those distributions in the simulation for this purpose. One of the things I find particularly early, I'm early in a modeling effort, I don't know the numbers. I don't know how long something's going to take. I don't know how much something's going to cost. I don't know how many resources I really need. But I might have a guess. I can probably guess roughly what it is. Again, we used to call that engineering judgment. And then I kind of say, well, what's the worst case and what's the best case? So I find myself using the triangular distribution a lot for my Monte Carlo work. And that turns out to be something that is very common in behavioral analysis with people, particularly in people's capabilities. Because oftentimes that's about all the data points you have. I remember one time we were modeling a similar time when we used triangular distributions. We were modeling the network, the DISA network, and so they had a big model. They had the whole thing modeled in what was called OpNet at the time. It's Riverbed now, and and they could only get 3 points because it took that long to run to determine the latency of the overall system. And that was what, that's all I got was 3 data points. Excuse me. So anyway, so that distribution works out very nicely for very early on. As you get more data, particularly later in the life cycle, you should have better distributions, and you could use other distribution forms for that. Particularly from your design engineering work, oftentimes the results of design engineering will be a parameter that has a distribution associated with it. Monte Carlo works, again, using the same process model as before. What it does is it takes that distribution and it does randomly sampling of the variables and or the decision points. If you make the decision points probabilistic, it'll sample those randomly as well. And you run enough of these calculations, and then that basically gives you pretty good results as to the confidence level that you're looking for. I've been reading a lot about this lately, about what's that number of iterations. Numbers I'm seeing are somewhere between 5 and 20,000. It tends to be a pretty good number for these kind of models. In fact, I was just running one that I did where we were running it at least 10,000 times. Again, this very complex model. So you may have to run it many thousands of times. By the way, so in Innoslate, these actually run in the browser. So it really does depend upon the cores of the machine you're using. So if you're using a higher end machine that has like 8 cores, it will use all 8 cores. And so the Monte Carlo calculations, it'll create 8 different runs that's running through and parallelizing the simulation. So it can go very fast the more cores you have. Okay, so how does scripting enhance simulations? So, scripting provides a means to determine particularly how decision points operate. That's one of the big ones you will find you'll be using scripting for. And also perform simple functions that affect the timing, the resources, or other parameters of the model. So you'll see that as you go through. Innoslate auto-generates common scripts. But then they can be edited by the user if desired. So for example, here I've got that OR in the middle there, and in there's a probability script to it. You just type in 95 and 5, and it actually does the scripting for me. In fact, what it does is generate this script you see below. You probably can't read that very easily, but you can easily go into one and take a look at it and see. It's as soon as you have submitted that script becomes available as one of the drop downs. Rather than the OR probability, you pick the script option, and you can see the script there. We just added a new feature in 4.7 where you're basically making it read only until you decide you want to edit the script. So you don't accidentally touch it and break it. It's always something that always can happen with code. If somebody accidentally is typing, I know I find myself do this, typing and having issues with it. So anyway, we're going to talk a little bit more about that in a minute. But this is really a very simple, low to no code. For you, it's no code because again, you're just using this little user interface we've created for it, but we're creating the code for you. Now that's useful because now you can go in and edit that code and add information to it and do other things. We're going to talk about that just next. So there is a scripting guide available. Currently, it is on a website, our Innoslate Help Center. It is being migrated as we speak to a new site. So I could give you the URL for this right now, but that wouldn't be much good because we're going to be putting out a new website here very, very soon. So hopefully, if you are looking for the Help Center and looking for other things, it'll be more obvious when you go to innoslate.com. Anyway, so scripting guide is available as an online resource, and this will still be there. It provides insight into how to use and build the built-in scripts, because that's the first part of it. Goes through them, explains them, shows you the code that gets generated, all that kind of thing. And it also starts talking to you about how to build more complex scripts. and particularly it documents all our simulator APIs. And yeah, it's a little fuzzy, but that's a set of the sim APIs. There's some other things further into it as you get in deeper in terms of working objects and doing things there. So again, and it also provides examples of using these APIs all the way through it. So again, this is a good resource for you if you're kind of wondering how to do something and you're not sure. Particularly if you're system engineering, you've done a little bit of coding. This isn't too hard. I've certainly I've been programming most of my life, but it's been a while since I've gotten into some of these things, and this was a fairly easy to pick up language. It's JavaScript, so is the underlying language. So we have a good code editor underlying it to also to help you get to it. So I think you'll find it's not too bad. If you have problems, definitely contact support, and we'll be glad to help you get going with it. So let me give you an example of one of these enhanced ones. So a common problem is I need to synchronize ORs. The reason is I have a model and I have two assets, and asset one there makes a decision and asset two has to react to that decision. So that's what this scenario is. So, and that's a very common thing to have happen as soon as you start recognizing you've got more than one actor in the system. You're going to probably be building something looking like this, and that's a real hard one to do a built-in script for, because of course you have to. It's dependent on two different objects. It's got I/O involved into it, so there's a lot of things there to generate that for you would be very difficult. So we'd love to if we could. We would if we could, actually. So the first actor, if I click on that first decision point, let me go back, make sure you understand what I'm talking about. So at P1, decide asset one makes a decision. So it's going to go randomly. So that it's using that random script, and then we just added in this idea of a global set. So we're making, if it's the less than 50%, we're going to decide to go down the true path. If it's greater, if it's between 50 and 100%, then we would go down the false path. So again, that decision, so it's a no decision. So again, that's just was fairly arbitrary, just decided that way. We could have done it the other way. Actually, no, it has tied it to the yeses, and so it's clear that's the right way to do that one. Anyway, so again, if you have a different probability distribution, like if it's 95-5, you'd see different numbers here. So in the R factors are less than or equal to 50. And I also have a print in there, so I can print to the console, and so I can see what decision was made, and I can kind of track it that way. Again, that's helpful for debugging purposes. On the return, you notice there's a very long number there. That number was auto-generated by the tool. If you're doing these by hand, you don't need that number. You could just put in the yes, whatever that value is, you know, in the decision. So, okay, so I hope that's easy to understand. It's fairly easy to read. I didn't put in a lot of comments in there. Probably should have made it even easier to read and understand. But hopefully that's a simple enough set of capability there, that code that it's not that overwhelming. Okay, so now that trigger is used to keep the second actor from making the decision before the first actor is completed, because of course it would make no sense, right? If you're going to react to a decision, then you want to wait for that. And so again, if you're not familiar with the execution language here, each branch there, both of them are enabled, so they could execute unless one's waiting for a trigger. And so that's how that works. So N1 there is making the decision in reaction to whatever P1 decided, so asset one decided. And that code looks like this. So again, now I had to go through and do a little bit more work. I gotta go get that global variable, that decision variable, and get its value, and it's true or false. So if I'd start with the probability script, which is what I did here of that, then I replaced the R less than or equal to, again, let me show you what I'm talking about there. So R is the random variable. So the R less than or equal to 50, I don't need any more because I know it's either true or false. So that's what D is giving me. So I got the D is true or false. And then so I would go down whichever path is correct. And again, you can see yes reaction and no reaction are the path names, and that long number is not relevant to you. It's something we auto generate from the information that we have in the database. Okay. So I hope, again, that gives you a very quick overview of the kind of scripts you might be writing if you need to. If that looks really hard, get some help from some code developers, but it is fairly easy to learn over time. I learned several scripting languages off of other tools over the years and found it to be very valuable to know how to do that. And so again, you don't have to do a lot of code, just a little bit. Okay, so how are costs, timing, resources, and physical constraints used in simulations? So the cost, timing, resources, and physical constraints can be added to the simulation to add realism and address the key goals of the system's engineering. It's optimization of cost, schedule, performance. That's what we're trying to do. Performance comes in a number of ways in the modeling. A lot of it's the timing. If you look at many of your metrics, if not most of your metrics, are time dependent types of things. Time of flight, time to target, on and on. So time is a major part of that. So that's a key performance parameter. Other resources though, like size, weight, power, consumption, those kinds of resources can also be used and modeled as part of your performance modeling. Of course, there are constraints that come with us, and so things like, and I'll actually say that more in a minute. So we go to the next thing. So fixed in cost terms, we have fixed. You can add distributions, and you have hourly costs that can be added to any step. So that's actually directly associated with the action duration. Is one of the ways. So that's that timing you can add to each one of them. I'm sorry, that's the cost of it. Oh gosh. Timing is the next thing. Again, that can also be a distribution attribute. It's duration attribute. It's fixed or distribution. Resources can be produced, seized, or consumed by any step. That's useful. Again, if I'm using a lot of water, and my tank starts running dry, I need to go back and refill the tank. So again, that can help you make decisions as well. So that's one of the options. That's one of the standard scripts you'll see that we have in the tool, and it's available. Physical constraints. This is a really important one. So we have the concept of latency capacity of a conduit. So the physical pipe, that something's going down, that has those parameters to it. So latency is the delay time it takes to transmit, and and then the capacity is the bandwidth. It's the IO. It's the size units of the same units as the IO. You want them to be the same, and then that has that size per unit time. So again, those are helpful in terms of being able to look at that and look at that delay. So what that ends up doing is you get a latency from the delay you get a delay from the latency, and you get a delay from the capacity of taking the time to transmit this large body of information, perhaps. So again, if that's helpful for you. Again, there's some really good discussions of that in the guide. So costs. How are costs, timing, and resources still used again? So looking at cost elements a bit more in depth here. So you can associate a cost entity with any step. Okay, so again, there's a simple relationship. It's called incurs or incurred by. Okay, so a cost is incurred by an action. An action incurs a cost. Okay, so in that, you can see, so here I am, I'm clicking on this RM 1.5 step, which is perform contingency operations. This is the failure mode. If there's a problem, I'm going to go down this failure mode, right? And so that's a branch in there. And so in there, it's a little hard to read here, but you see it incurs a cost. So if let's say I wanted to add a cost to that, I would just go click on that. I'd come to the sidebar, I'd click relationships, and then add. And I could add a new cost right there, and I'm good to go. Or if I have an existing cost that I want to associate with it, I could do that as well. So let's look what a cost element has in it. So in it, it has the name, number, description. Of course, that's everything. Every object in the database has those three attributes. The amount that is there, that's the value, and again, that could be a distribution. You just type equals and then start the distribution word like triangular TRI, and that'll pop up for you. You can fill that out. And then put in the units. Always good to have the units and to have consistency. Most of the time, if you're in the US, it's going to be dollars. It'll be euros in Europe. Back in Britain, it'll be pounds again. Anyway, so fixed rate, and again, you have other. You got that. That's where you put the whether you want a fixed or a variable rate, per hour rate. So that's put in there, and then the category. Again, these are categories that are standard categories, and a contract type if that's appropriate too. So again, those are things you don't have to fill out, of course, all those things. The main thing is the amount and the units. So timing is put into the duration attribute of the action. Again, here we go. So they're clicking on 1.3. If you look at the attribute list there, there is duration, and there is actually a triangular distribution there. Maybe you can't read it very well, but it has a range of 10 to 20 seconds, and so the median point is of the middle part of the triangle is at 15 seconds. So again, very simple one that you might use for something like this. And then resources. Now resources, again, this gets a little more complicated because it requires both a resource allocation, a relationship. So there's a relationship, in this case, consumed by or seized or produced, depending on which one it is you're looking at. This is particularly the one I've clicked on. I've clicked on the resource itself, the water, and it's consumed by. Each one of these has a normal distribution associated with each of the firefighting teams here, the RM 1.4931 through 4. That's in that parallel there. So it's associated with each one of those. So it's actually being consumed. So this is a water supply that's being consumed by the firefighters. Kind of makes sense, right? You also have a relationship attribute associated with that, and I'm sorry, that's that amount. That's where you get that normal distribution. So so there's a little bit more complexity to the resource model, but again, we've made it as simple as we can, and you still put in the information you need in there. So I think again, it makes it fairly easy. That you'll see the modal for this. I'll probably show this in the demo portion in a little bit more depth for you. So how do system simulations work with design engineering simulations? Again, this is that big focus that's going on today with the whole digital engineering, digital twins, digital threads, digital ecosystems, on and on and on. And I'm on several committees at AIAA and INCOSE and NDIA. They're trying to define some of these terms and make them make a little more sense, but it's quite a challenge. Frankly, but it is something we've been doing for a long time. I know I've done it my entire career, done this equivalency. So it's not a new idea. It's just we're kind of come up with new terms for it, and it's because we're able to do so much more in simulation than we could back when I started back in the late 70s doing this kind of work. Anyway, so the idea is to create simulations of the system that mirror the behavior of real systems, and that's always your goal. You're trying to make that work. And again, this comes back to that calibration I've got to make that really mirror. I better be calibrating it to the real world, because there's only so much we can model. Oftentimes we don't even know the physics well enough to model it into that level of depth. So as you get particularly in the design engineering physics-based simulations, there are limitations. If you have a 3-degree freedom model, for example, versus a 6-degree of freedom model, you've made an assumptions, you've made some abstractions. The 3-DOF model is not as good as the 6-DOF model, but it'll run faster, and maybe that's all I need in terms of whatever my constraints are of the system. So that may be okay. So these are the trade-offs we make as we're doing these engineering calculations. There's been kind of this big push to try to integrate all these levels from the mission all the way down into design engineering of simulations. And I've watched that over the decades try to happen, but most people don't realize that the simulations really operate in different time regimes. Oftentimes, I might be working in milliseconds in the design engineering work. I'm working in the system, I might be working in seconds to minutes. And in the mission, I'm working hours to days to years potentially. So again, very different time regimes are being involved. And oftentimes the higher level fidelity models in the design engineering physics-based models take time to run. I mean, significant time to run sometimes. There's a reason they run them on high performance computing assets like Craze and other things that are out there today. So again, that's not that easy to integrate. And so what we do is we take to integrate them. What we're integrating really is the data, the output of those tools. So we use that information to help make decisions at the higher and higher levels. And so that's where trying to do this integration is extremely difficult. Now we've done some things with this, so we think we've got that nice sweet spot between them, because what we've done is we integrated first with MATLAB and STK. So those are the main design engineering ones we co-simulate with. Okay, so this means that as I'm executing the Innoslate simulation, I can execute these other two tools simultaneously and use them to make calculations that I can't make in Innoslate. Don't even want to begin to try to. So if you have a MATLAB model that's very detailed, that's very important to what you're doing and what a particular operation takes, then you can put that into Innoslate you can execute it through Innoslate and then tie it together with your system level model, or even again with STK, you're maybe at the mission level. So again, these are tools that are really helpful for that. Okay, so MATLAB again provides access to existing mathematical calculations, and particularly that can affect the timing. The example I'm showing you here is a MATLAB post and get. Those are the only two APIs we have for MATLAB. Seems to be all we really needed. If there's something more we need to add to that, let us know. But there's some other. Those are how we put it. So you do a post. And then that executes, that sends the command to MATLAB, and then it waits for the MATLAB activity simulation to complete, and the output from that is then brought into Innoslate. Now, that output can be an array, it can be all kinds of things. It's not a simple, single number or variable. It can be quite complex. It's an object coming back in. So again, it could be something pretty significant in how you use it. In that case, it was doing it was calculating some kind of resource and bringing that resource value in and adding it to it, setting it. So STK though is a little more complicated. We have a larger set of APIs to use its capabilities. It's a tremendous geospatial analysis tool. Again, if you're not familiar, STK is an ANSYS tool. ANSYS bought AGI, who was the original developers of those. And by the way, they rebranded AGI to being ANSYS Government Initiative. So they're doing a lot of their more U.S. government work through AGI now. Anyway, again, this gives us some tremendous geospatial analytical tools, and again can provide that constraints on the timing due to the geospatial nature. So in other words, if I'm waiting for an asset to get into a specific position before it's going to transmit the information, then that's going to delay the overall model as it has to move into that position. So again, very, very valuable. We have some great examples of this in our lunar rover example. Now, one thing, there is a constraint on this. It only works in discrete event simulation and only with the enterprise version. And there's a variety of reasons for that. First of all, we don't own either of these tools. So we can't exactly make them available to you on the cloud directly. There are cloud systems. There is a cloud system right now that has that ability to take its enterprise version and use it to execute MATLAB. We haven't done SDK on that one, but it's available. So there are ways to get this done on a cloud system. So don't be afraid that we're going away from cloud computing, because we're not. Anyway, so Innoslate can also access CSV data files. Okay, so we actually can import output from other tools, other simulation tools, that's in the CSV format that we read in, and then use that to do different things. And we've proven that capability. Also, you can hyperlink to other internet addresses for co-simulation. So we built a simulator that would check the weather before it was making a decision. So if it got to be above a certain side, it would make a different, certain temperature. It would go one path, and then another, and lower temperature go another path, that kind of thing. So again, it depended on that internet resource of what the current outside temperature was. So there's a lot there. Okay, so I think it's really our Q&A time. Hopefully we've got some questions going on. Taylor, do we have any questions? And I'm going to bring up the tool itself while the questions are being asked.
Yeah. So we received several already. If you haven't done so, please send your questions through the panel on the right. Dr. Dan will answer as many questions as he can before our time is up. So someone asked, can you simulate smaller sections of the diagram?
Yes. So usually the way to do that, just give me 1 second. We just added two-step authorization here, so I have to do that. You have 10 seconds to use that number. Anyway, so the way you do that is here in a decomposition. So you would select a portion of it and have that ready to simulate. And so here I would come in and I could execute this one. Now this will execute because there are no triggers from the outside. This is just an optional in here. If this was a trigger, okay, let's just make this a trigger. If that was a trigger, then the execution wouldn't occur because it would be waiting on that trigger. Something has to generate it from the higher level. But in this case, we have it optional, and so that allows you then to also simulate it directly and just that portion of the problem. So does that answer the question?
Great, yeah. Next question is, how is the simulation cost determined? I think they might want to see.
Sure, sure. So let's take a look at that contingency operations when maybe you'll see it more. So here, I come over to relationships, and I can see that relationship associated with it. There's incurs a cost. So here's that cost element. Again, if I wanted to create a cost, I would do it here, or I'd add it. We already have it here, so that's easy enough. And then if you do add a new one, it'll actually come up with the attributes. You can just fill in right there, and so you don't have to do anything else here. But then this also lets you come in and pick the labels and things like that as well, if that's desirable to you. Again, very easy. Here's that fixed or hourly rate. We do, since we use this simulator for project planning as well as regular design engineering kinds of activities, we have that kind of hourly modeling as well. Any other questions?
Someone asked at the beginning, do simulators integrate with MATLAB, which you covered? If there was anything else you wanted to add to that?
So we've looked at other tools, but right now we haven't been able to we haven't had the interest level for people to pick other tools to use. But if there are other tools besides MATLAB, that certainly would be good to see. Good to hear if that's something of interest.
Those are all the questions I have for now. Did you want to demo anything else?
So I guess let's walk through a couple more things here. Again, I just showed you the cost aspect. Here's the scripting. Again, you probably couldn't read it very well, but here's that ability to pick it's a resource script or a probability or a script itself, directly script. And once you do the submit, we have kind of a default. If it's 50-50, you won't see the script, okay, unless you submit it. And then that's when the script will be shown in that scripting field. So that confuses people a little bit, but that's kind of in the background. We just assume a default 50-50 otherwise. But this shows you how it was built in this capability here to do the random numbers. And so it just gives that a random number, and then you look the value and pick which path we would go. So it says 95% of the time, I'm going to go down the normal path. Again, to edit, I'm sorry, I should have. To edit the script, you just click that and confirm you want to edit, and now you're here. And so again, we put that in just to make sure that there wasn't a problem. You can also add code stubs on start, on prompt. You only have one on end, one of each of these things in here. So on prompt is very interesting. Again, it really only works with the discrete event simulator, as you might imagine, but you can use that to prompt users for information. So we designed that so you could do like tabletop exercises using the simulator, and it could actually fuel that kind of capability. Let's see. Another thing in here, again, the guides. Go to the Help Center here real quickly and show you the guides. So here's where you get your scripting guide. Also, here's your MATLAB STK guide. Both those are here and available. Just select in there and you'll see the scripting information about the specific scripts that's available. Also with that, there is also the user guide, and you can go to the simulators, and it talks a lot more about simulator controls. And this is where you can get into seeing how the capacity and latency affect the duration of the execution of it. So things like that are in here. Concept of cloning's in here. That's something we haven't talked about, but it's actually a very interesting concept and very useful at times. Again, here's your cost analysis. Again, some simple scripts. By the way, this shows you your wait times, and most of the time you see yellow, but you can have these other ones as well. Gray, active blue, you see those, but some of the other ones, orange, maroon, green. So sometimes you'll see those pop up, colors, resource weight. And very useful information here. It's available on the website. Let's see, that's kind of about it. Again, if you need help with scripting, please contact support. They'll be happy to get you going, get you started. You can find a lot more. By the way, there's more simulator script here, but The scripting guide we have is much more detailed and provides many more examples than this does, so, in the Help Center. And here's that STK MATLAB guide. Let's get you into using STK. Okay. Is there any other questions or comments? Or
I don't see any questions, but I'll go ahead and close this out.
Okay.
We would like to thank you again for joining us today. As a reminder, we'll be following up with you very soon to send you a link to the recording, the presentation slide deck. We hope you can join us for our next webinar, Getting Started with MBSE, a data-driven approach with Innoslate on June 14th at 2 p.m. Eastern. If you can't join us live, be sure to register to receive the slides and the recording. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.